So, you were curious about how vec works in Rust. You look up the docs, click source, and this is what you see. Whoa, too complicated. Well, first, a lot of this information is unnecessary for understanding vec's functionality. This code gives the compiler and versioning teams extra information to work with. For our purposes, we don't really need to see it. From this point on, I will leave out this information from the code I show. If you want to see the full extent of Rust source code, or even just specifically vec, I will link it in the description. If you're like me, and you've scoured the Rust standard library to try and understand it, you will have noticed code like this on basically all of the provided collections. My goal in this video is to have an in-depth look at the global allocator provided by Rust. However, I won't be diving into the actual implementation of the allocation. This will mostly be an analysis of what I think is a beautiful API design, Rust's global allocator. Let's get started. We begin with this bound on the vec struct. In Rust, generic types only have the behavior specified by the traits we bind to them. The generic type T does not have bounds and can therefore be substituted for any type. A is bound by the allocator trait. This means the user creating the vec must supplement a type in place of A that implements the allocator trait. However, a default value is provided if the user does not supplement one. Global. Let's see what behavior is specified by the allocator trait. Allocator is an unsafe trait because it requires the programmer to ensure that the implementing type follows rules that cannot be enforced by the compiler. In the case of the allocator trait, this is pretty much its whole thing. Allocators define behavior that has fine control over the program memory, so they have to follow precise rules, particularly rules unenforceable by the compiler. The allocator trait requires the implementing type to define two methods, allocate and deallocate. There are 5 other methods that are optional to override, but they are beyond the scope of this video. We'll begin by analyzing the allocate method. It takes in a reference to itself, the implementing type. It also takes a layout. Well, what is a layout? Before we explain layout, what does all of this mean? This is a derive macro. It allows the programmer to derive traits they want the specified type to have. In this case, we derive a few. Copy, which says that the type is cheap to copy in memory. Clone, which is a prerequisite of copy and means that the type is able to be cloned in memory. Debug, which generates a debug console display for the type. Partial eq, which means that the type has a partial equivalence relation, meaning you can check equality between it and another of itself. This one will show up later. Eq, which means that the type has an equivalence relation. This is complicated math stuff, so I'll leave a link in the description for anyone who wants to dive deeper into these two traits. Lastly is hash, which means that the type can be hashed, turned into a fixed size value, typically an integer. These derive macros will be above many types throughout this video. If you're curious what behaviors any of them define, I encourage you to search them on the Rust standard library, which will of course be linked in the description. They can provide a much better explanation of their own traits than I can. Alright, we can finally get back on track. A layout is used to request a block of memory. This block of memory is measured in bytes. Layout has 2 fields, size and align. The size field is a usize that specifies the size of the requested memory block. A usize is an unsigned integer with a size dependent upon the operating system. On a 64-bit OS, usize will be 64 bits. On a 32-bit OS, usize will be 32 bits, and so on. The align field is an alignment that specifies the alignment of the layout. You may ask, what is an alignment, and what does that mean? The Rust standard library team left a helpful comment describing a property of align. It is always a power of 2. This represents where in memory a type is allowed to be allocated. Each type in Rust has an alignment which is always a power of 2 and is usually the same size as its size in bytes. I will link in the description an explanation of alignment if anyone is interested in further reading. I'd highly suggest it, it's confusing. Let's peer into the implementation of alignment. So alignment is simply a wrapper struct around an enum called alignment enum. Quick aside. Wrapper transparent simply means that the memory layout of alignment, meaning its specific bit pattern in memory, is guaranteed to be exactly identical to that of alignment enum. This means that the two types can be trivially turned into one another. Now that we know alignment is the same as alignment enum, let's check out alignment enum. Oh, okay, hold on. That's a little too much to digest all at once. Much better. We can see that alignment enum is an enum with 64 variants, with each variant being the number 1 left shifted by 1 more bit than the last. This symbol means left shift. I'll explain exactly what that means in a second, but first, why 64? Where did that come from? I left out some crucial context. This is the version of alignment enum configured for a target pointer width of 64 bits. My code editor brought me here because I'm using a 64-bit operating system. Repr U64 simply means that the enum variants will be represented by unsigned 64-bit numbers in memory. Otherwise, the compiler could optimize them to fit into a smaller space, which would defeat the whole purpose of this enum. There are also 32-bit and 16-bit versions of alignment enum depending on your compiler configuration, typically decided automatically based on your OS. Now, here's what left shift means. In the computer's memory, alignment enum is stored as a sequence of bits, zeros and ones. The number 1 can be represented by all zeros followed by a single 1. Shifting these bits to the left, then, is just moving all of the bits one position to the left and filling the missing spot with a 0. Here, we start with 1. Shifting left, we get 2. Shifting left again, we get 4. This pattern continues to the largest enum variant. In the case of a 16-bit configuration, this is 32,768. Notice that all of the enum variants are powers of 2. This is exactly the rule outlined in the layout documentation. Very clever. Alright, now we understand what alignment enum is and how it works. Notably, since alignment enum is functionally identical to alignment, we also understand how alignment works, because of repr transparent. As said before, alignment is contained within layout, which is a parameter of the allocate method. The return type of the allocate method is result, non-null to a slice of U8, alloc error. We will build up an intuition for what this means from the inside out. First, let's find out what non-null to a slice of U8 is. Looks complicated, but it's not. T (sized) means that the generic parameter of non-null doesn't need to have a size that's known at compile time. This means unsized types, like slice of U8 or stir, can be T. Repr transparent means exactly what it meant for alignment. The memory layout of non-null is guaranteed to be the same as that of *const T. But what is *const T? *const T is a raw pointer to the memory location of T. In memory, this pointer will be a U size containing the memory address of our data. Const means that the data pointed to can't be mutated by this pointer. The other variant of a raw pointer in Rust is *mute. Pointers have some special behaviors, the main one being the ability to be dereferenced. Dereferencing a pointer means going to the memory address it stores and reading or writing to the data at that location. To be dereferenced, a pointer must be non-null and aligned. A null pointer is a pointer that points to the address 0. A null pointer cannot be dereferenced because the null address, 0, is not valid to read or write to in any circumstance. The non-null struct ensures that its raw pointer is never null, meaning it can always be dereferenced, hence its name, non-null. We will see exactly how non-null ensures its pointer is never null later. So part of the return type is a non-null pointer to a slice of U8. The square brackets around U8 mean that it is a continuous segment of U8 in memory, called a slice. This is not the same as an array because we do not know the slice's size at compile time. This is why we use a pointer to the slice. This will make sense after we discuss the rest of the method signature, where we will deduce the purpose of the allocate method. Next, what is alloc error? Clearly it's an error of some sort. How does that work? Pretty simple. Alloc error is a unit struct. Since it contains no data, it is technically nothing. This is a concept in Rust called zero-sized types, or ZSTs. This is a type that contains nothing but represents something. I'll link an explanation of ZSTs in the description, but the gist is that they enable some special compiler optimizations. Alloc error, unsurprisingly, implements the error trait, which is just a marker trait noting that alloc error is indeed an error. Lastly, alloc error implements the display trait. This trait defines how to display a type when printed to the console. In the case of the alloc error struct, the console will simply display memory allocation failed. Very frank. Now we know what alloc error is. Okay, so the return type of the method seems to be a combination of non-null to a slice of U8 and alloc error. What is this result type that combines them? Let's find out. Result is an enum that has two variants, OK, which contains the success value, and error, which contains the error value. Basically, the result enum can either be its first value, OK, or its second value, error. OK is the value we want, and error is the value we don't want. This is not a strict contract, however, and some functions will opt to use the error value to provide non-error information, such as slice's binary search method, which returns the found index on success and the nearest index on failure. That's the method signature of allocate explained. Let's recap. The method has two parameters, a reference to self and layout. The method's return type is a result enum with OK variant non-null to a slice of U8 and error variant alloc error. From this method signature, we can glean the overall purpose of the method to, surprise surprise, allocate a block of memory with the size and alignment specified by layout. After trying to allocate the memory, the method either returns a pointer to the beginning of the allocated block or fails and returns an alloc error. Pretty simple when you map it all out like that. A nice part of this design is that Rust forces you to handle an allocation error rather than ignoring the possibility altogether. It's good practice to cover all possible scenarios in programming. This behavior is encapsulated inside of the allocator trait. Vec requires an allocator to decide how its memory will be requested and freed. Global is Vec's default allocator. It is generally the default allocator for the Rust language. Global is simply a unit struct. It holds no data and is thus a zero-size type as explained earlier. To use global as an allocator, we implement the allocator trait on it. This means defining the allocate and deallocate methods required by the trait. 4 of the other trait methods are overridden for the global allocator, but they are beyond the scope of this video. Let's start with how global defines the allocate method. First, inline means that the compiler will try to put this method's content inside of the calling function, rather than inserting a jump to the method. This can speed up execution by enabling greater cache efficiency and more optimizations. Many methods we will analyze have this attribute, while others have an even stricter version, inline always, which ensures inlining happens no matter what. Note that inlining functions can increase the size of your executable, so it is best used on small functions. Alright, back to the allocate method. Remember, this method is meant to allocate a memory block and return either a pointer to the allocated block or an error. The content of this method simply calls another method, global's alloc_impl. It takes in the layout and a boolean, in this case, false. Spoilers, this boolean specifies whether or not the allocated memory is zeroed. There is another method defined by the allocator trait called allocate zeroed. See how the boolean is true in this one? For now, we will just look at allocate, but allocate zeroed will make a guest appearance. So, let's dive into alloc_impl. The method signature of alloc_impl is identical to that of allocate, but with an extra zeroed boolean parameter. The method begins by matching layout.size. Matching is similar to a series of if statements, checking if the specified value is equal to the provided values and running the code under that match. Here is an identical version, which explicitly defines size as a variable and uses if statements to emulate the same behavior as the match. So, what even is this mysterious layout.size? It's just a simple accessor method. It simply returns the size of the layout. Remember that size is a usize specifying the number of bytes requested by the allocator. So, we return the layout size using the accessor method size and plug it into a match statement. First, we handle the scenario where the provided size is 0. In this case, we are allocating a ZST. Let's start from the inside out. Let's start by finding out what layout.dangling means. This method signature takes in a reference to itself. Self in this scenario is layout, which we can see here because we are implementing methods on the layout type. Remember to check which type is implementing a method since it informs you what self is. So, the method takes a reference to a layout and returns a non-null dangling pointer to a U8. A dangling pointer is a pointer to invalid or deallocated memory. We can glean from this signature that the method intends to create a pointer to the beginning of the requested memory block without actually allocating memory. Again, let's start from the inside out. Self.align is another access method for layout, this time for its other field. The method returns a usize that is the align of the layout. However, align isn't a usize, so it must first be converted to a usize. The asUsize method takes an alignment and turns its contained alignment enum into a usize. Self.0 is the notation to access the first element of a tuple. Alignment is a tuple struct with one element. More reading on tuple structs will be linked in the description. So asUsize returns a usize representation of the alignment. We get the align and then convert it to a usize to be returned to the caller. However, why should self.align return a usize? Shouldn't it return an alignment? Wouldn't that be more in line with the functionality implied by the method name? Let's see what changes would have to be made if we accepted this notion. We could change the method signature of align to return an alignment. Now it is an accessor method that simply gets the alignment value of layout. This requires us to change the dangling method to explicitly use self.align.asUsize, having to convert the alignment to a usize every time we use it. I'd say that the Rust team made the right decision. They likely wanted to obscure the implementation details regarding alignment from users of the Layout API. This is common in API design. Next is this function with a super long name, create pter without provenance mute u8. Notice that I said function and not method. That's because this function is not implemented on a type. It is a standalone function. Let's check it out. This function takes in a usize called addr, short for address, and returns a mutable raw pointer to t. We can't really deduce what this function is doing from the name though, because it uses this confusing term, provenance. Luckily, the Rust standard library authors left a helpful comment explaining what the function does. They write, "Fix me, strict provenance magic," and explain that the function is magical. In the documentation of the function, they explain that this function is part of an experiment they are doing called strict provenance, which is a more explicit way of treating pointers and their origin. I will link in the description some more in-depth reading explaining the strict provenance experiment and exactly what it means for Rust's memory model. For now, we can simply say that this function takes a memory address and creates a mutable raw pointer to that memory address. The specific behavior associated with provenance is beyond the scope of this video, but we will see this function many more times, so keep all of that in mind. So, the function takes a memory address and returns a pointer to that address. How? All it does is transmute addr from a usize into a star mute t. But what is transmute? Transmute is a compiler intrinsic that simply reinterprets the bits of one type as another type. It makes no other changes. Simply put, it snaps its fingers, and now the usize is a star mute t, like magic. The compiler inserts the contents of this function at compile time because its behavior is platform dependent. Such is the life of a compiler intrinsic. In this case, it reinterprets a usize as a mutable pointer. This is guaranteed to always work because every valid usize value is also a valid pointer. The authors specify that safety constraint here. Unsafe functions in Rust simply indicate that the compiler cannot ensure its memory safety, leaving that responsibility to the calling function. Unsafe functions will define a contract for the caller to uphold. In the case of transmute, the input's bit pattern must also be a valid bit pattern for the output type. This is trivially true for any usize and star mute t, so the safety contract of transmute is upheld. So the function takes a usize and returns a pointer to that address. This means we take the alignment value specified by the layout and turn it into a pointer. We have created a raw mutable pointer to an address that is a power of 2. Next, we create a new non-null pointer using the aforementioned raw pointer. Non-null new unchecked has a method signature that takes in a raw mutable pointer and returns a non-null. The unchecked suffix is a common Rust API pattern that means safety checks are omitted. We will see the checked version of this function later. This macro, which asserts the safety guarantees necessary for non-null, does not exist when compiling in release mode, so we can ignore it for now. We assume pter is non-null and construct a non-null using it. Pter as underscore lets the compiler infer what pter should be cast as. If you have more information about exactly what as underscore does, please leave a comment because I've been trying to wrap my head around how it works and all of my Google searches come up empty. So, we've used a raw pointer to create a non-null pointer. We return this non-null pointer and the method is complete. We can now explain what the dangling method does. It creates a non-null pointer to the alignment specified by the layout. It is a non-null pointer to a power of 2. So we have a non-null pointer to a power of 2. We pass that dangling pointer into this method, non-null slice from raw parts. This method is extremely important to allocation in Rust. Let's see what it does. The slice from raw parts method signature takes in data, a non-null pointer to t, and len, a usize. Its return type is itself, a non-null pointer to a slice of t. Basically, this method takes a non-null pointer and a length and turns them into a pointer to a slice. This is called a wide or fat pointer. This means it's a pointer that contains both a memory location being pointed to and a length. This pointer contains the size of the pointed to memory at the cost of extra memory usage. So this method turns raw parts, a pointer and a size, into a slice pointer. Let's discover how. Strap in. Again, we'll start from the inside out. The asPter method simply takes a non-null pointer and returns its underlying raw pointer. It does this by casting its pointer field to a mute raw pointer. As a reminder, the pointer field of non-null is a const raw pointer. We cast the const raw pointer to a mute raw pointer. I will link more reading about raw pointers in the description that may further elucidate when and why to use const and mute raw pointers in Rust. So, the asPter method is simply an accessor method, and we have turned data into a raw pointer. Next, we have a function with the same name as our current method with an additional _mute at the end. Let's see what it does. This function has two parameters, data and len, a raw pointer and a usize respectively. Its return type is a mutable pointer to a slice, a wide pointer. This function simply calls another function with the same parameters, from raw parts mute. However, the parameters of this function are different. They have additional constraints. The first parameter, data pointer, is a mutable raw pointer to impl thin. Impl thin can be any type that implements the thin trait. Well, what is the thin trait? Thin is an alias of a different trait. Specifically, thin is a pointee with an associated unit type. Unit is the main zero-size type in Rust. It is represented by the open and closed parentheses. Okay, well, what is a pointee? Pointee is a trait that is automatically implemented for all types in Rust. It describes what metadata a pointer to the pointee must have. For example, pointers to slices, as seen earlier, have usize metadata to store length. This is called a wide pointer. This is why the thin trait has unit metadata. Their metadata is zero-sized, and they are called thin pointers. A thin pointer consists solely of a memory address. There is another metadata possibility called dyn metadata, but that is beyond the scope of this video. Once again, I will link the Rust documentation where this is explained in depth. So the metadata associated type of the pointee trait determines the size and behavior of pointers to the implementing type. Thin, then, is a pointer with no metadata because unit is zero-sized. Now that we understand thin, we know that data pointer is a pointer to any type that does not require extra pointer metadata. Metadata, the other parameter of this function, looks complicated, but we can work through it. Understanding complicated things is fun. T as pointee, metadata, is the associated type specified by the pointee implementation on T. When implementing the pointee trait for T, it must have an associated metadata. So, this type is T's metadata. Here, T is a slice of U8, so its metadata is a U-size length. I will link the Rust book section that outlines the advanced trait features for a more thorough explanation of this concept. Now that we know the types of the parameters, we can check out this function call, aggregate raw pater. Okay, so, lots of generics. Let's try our best to understand this. The parameters of this function are d and m. The return type is p. D and m have no constraints on them, but p does. P must implement aggregate raw pointer. Let's see what that is. Aggregate raw pointer is a trait with a generic type D and an associated type metadata, similar to pointee. The trait has two identical implementations, one for const pointers and one for mute pointers. A good way to understand this trait is to imagine that it gives metadata to a thin pointer. It aggregates the metadata m to the thin pointer d into p, which is then returned to the caller. It turns a thin pointer into a wide pointer by attaching or gluing the metadata m to the pointer d. Of course, this is a simplification, but it's the best explanation that I could come up with. So the entire function signature tells us that we give the function a pointer d and metadata m, and the function aggregates them into a pointer p. How does it do this? Well, it doesn't. This version of the function is unreachable in normal code. Then how does the global allocator do anything? Did our exploration end at an unreachable function? Well, no. This attribute indicates that this is an intrinsic function of the Rust compiler that must be overridden. I don't want to go searching for its implementation, so I'll leave that as an exercise for the viewer. I believe in you. Now we know that this function takes a thin pointer d, metadata m, and returns an aggregated wide pointer p. This is in line with what we were expecting from where we started, slice from raw parts, where we gave it a pointer to the beginning of the memory block and the memory block's length. Let's zoom back out. We called aggregate raw pater and left the rest to the compiler. From raw parts mute takes a thin pointer and metadata and feeds them into aggregate raw pointer. The outcome is a wide pointer to t. So we called from raw parts mute on our data pointer and len usize. As before, the outcome is a wide pointer. This time, specifically, it becomes a mute pointer to a slice of t. Finally, we're back to slice from raw parts, and we've created a raw wide pointer to the memory block that stores its memory address and size. Our last step is to wrap that wide pointer in a non-null wrapper. We know that the pointer is non-null, so we can use the new unchecked method. As a quick reminder, here is what the new unchecked method looks like. Now we have a non-null pointer to a slice of t. So, we can now fully deduce what the slice from raw parts method does. It takes in a non-null pointer to the memory block and its length in bytes. The function returns a non-null wide pointer to the requested memory block containing both its address and its length. Now that we have the desired wide pointer to the memory block, we wrap it in the OK variant of the result enum and return it to the caller. All of that work was just for the case where the requested amount of memory is 0. The result will be a dangling wide pointer with a slice length of 0, so no allocation has taken place. Thankfully, we can speed up now that we understand some of the more fundamental functions. Next, what happens when size is a value that isn't 0? Let's explore both paths for the zeroed bool. If it's true, we call this function alloc_zeroed. Now I want to pause and say, look how cute my drawing of 0 is. Happy Halloween. If anybody would also want something like a speed draw or anything similar, let me know. Okay, so this function just calls another function called rust alloc_zeroed. For now, we're going to ignore this function and come back to it later. So that function is called when zeroed is true. What about when zeroed is false? Unsurprising. Well, let's see what alloc does. So, it takes in a layout and returns a mute raw pointer to a U8. This must be where the actual allocation happens. This line seems to ensure something about the stability of the Rust Allocator API, which is unstable. Let's uncover what it does. This function, readVolatile, takes in a const raw pointer to t and returns t. Sometimes the compiler will move operations to make them faster or more memory efficient. A volatile operation is an operation that cannot be moved or changed because other operations might rely on it. This is most notable in I/O operations because they might change the entire operating state of the program, so they cannot be moved. I will link this function in the description as the Rust team provides some extra information about what it means for an operation to be volatile. For our purposes, we can say that this function performs a volatile, bitwise copy of t. Similar to earlier, this code only runs in debug mode. It simply ensures that the pointer is aligned and non-null. We can ignore it. Here, we call an intrinsic function called volatile load. This function is a compiler intrinsic, similar to transmute. This means it is different depending on the operating system and the operating context. Returning, we have now read the value at the pointed to address. readVolatile is simply a wrapper around this intrinsic so library authors don't have to call the intrinsic directly. Now that we have read the value at rust no alloc shim is unstable, we can continue. I believe that this is simply to ensure backward compatibility with the old Allocator API. This API is still unstable and open to change. Anybody who wants to contribute, hit up the Rust team. Next, we finally call this function, rust alloc. This function is part of a bigger collection of allocator functions that actually call the global allocator. The authors call them magic symbols. Woo! The actual implementations of these functions is far beyond the scope of this video because I have no clue how they work. Check it out for yourself if you want. We can ignore many of these symbols for now and just focus on rust alloc, rust alloc_zeroed, and rust no alloc shim is unstable since we have directly interfaced with these symbols. They are all defined here as part of the magic symbols that are generated by the compiler to do their special job of handling allocation. Zooming back out, we realize we have found the end. The actual moment of allocation is here. The memory has been allocated and we have the pointer to the beginning of the memory block. That, or a null pointer if things didn't go to plan. We can see that this alloc function serves as a wrapper for the unstable Rust Allocator API. Raw pointer is now either a pointer to the allocated memory or a null pointer depending on if the allocation succeeded or failed. Moving on, we construct a new non-null pointer using raw pointer, but this time it's not unchecked. Time to find out how non-null ensures that it constructs a non-null pointer. The non-null new function takes in a mute raw pointer and returns an option of itself. Option is one of the most important structures in Rust. Here is the definition of option. It is an enum with either nothing or some value. So in the case of our function, we either return none or we return some non-null pointer. Here is the important check. If the pointer is null, we obviously can't use it to create a non-null pointer. IsNull handles this for us. Let's see how it's implemented. Whoa, it's long. Let's break it down piece by piece. There's a runtime impl function, and there's a const impl function. Both of these functions take in a mute raw pointer and return a bool. These functions are both put into a separate function as parameters, const eval select. We will get to that function after we explore runtime impl and const impl. Runtime impl is the first function, and from its name, we can deduce that it is meant to execute at runtime. It checks if pater.addr is equal to 0, which would mean pater is null. Let's see how the addr method retrieves the address of the pointer. Addr takes a pointer and returns the pointed to address as a usize. First, it casts the pointer to unit. This makes the pointer thin and means it is only an address. How does it do this? Well, it just does self as underscore, which lets the compiler infer which type the pointer will be cast to. In this case, it is cast as unit. Now we have a thin pointer to the specified address. Next, we transmute the pointer to a usize, just as we did earlier. As a reminder, here is the definition of transmute, which just tells the compiler to reinterpret the bits of src as a dst. So, we transmute to a usize, which gives us the address pointed to by the pointer. At this point, we check equality between the pointer address and 0, aka null. Now, const impl is different because it is a const function. This means that it is capable of running at compile time. So this does a null check of a pointer at compile time, which is more efficient than doing it at runtime. The isNull method is so long because the authors wanted to ensure it is as efficient as possible. The function does a special guaranteed eq check between pater and a mutable null pointer created by nullMute. If you are an experienced Rust dev, you may be wondering why this code doesn't look like this or this. The reason is that the unwrapOr and unwrapOr default methods are not so they cannot be used in this const context. With that out of the way, let's see how nullMute creates a mutable raw null pointer. The function signature ensures that it can only create thin pointers using the thin trait bound. First, we call without provenance mute, which we have seen before. This function creates a pointer to the specified address. Here is the function definition as a reminder. So we create a pointer to 0, which creates a null pointer. Next, we use from raw parts mute, which we've also seen before, to create a pointer with unit metadata. Here is the function signature if you don't remember. This function aggregates the pointer and the metadata into a new pointer with both. In this case, we aggregate a thin pointer into a thin pointer, so the aggregation seemingly doesn't do anything, and if I had to guess, it's likely just for compatibility or future-proofing sake. That is nullMute. It creates a thin, mute, raw, null pointer. Now that we have a null pointer, we compare it with pater using guaranteed eq, which is a const-friendly equality comparison. The function signature indicates that we are working with mute pointers. For code reuse sake, we cast both pointers to const and compare them using the const version of the same function. Since Rust has zero cost abstractions, this should have no overhead. Here is the const pointer version of the guaranteed eq function. It calls an intrinsic called pater guaranteed comp that was tailor-made for const comparisons of pointers. This intrinsic is interesting though. It takes two pointers and returns a U8 instead of a bool or Rust's typical ordering enum used in most comp functions. This function will return 2 when it cannot determine equality between the two pointers at compile time. Otherwise, it will return 1 when they are equal and 0 when they are not. I will link its documentation in the description because it gives a more in-depth explanation. So we have compared the two pointers at compile time and gotten one of 3 results. To make these results usable, the authors were clever and used option to create a 3-possibility output. None for an unknown result, some true for true, and some false for false. Let's zoom back out to where we compared the two pointers. The authors did a similar thing as before here. If the equality check couldn't decide, we just assume they are not equal. Otherwise, we use the found result. Lastly, let's see what this const eval select function does. Another intrinsic with lots of generics. This function, similar to other intrinsics we've seen, must be overridden. Even so, let's see what bounds are enforced upon the parameters of this function. The first generic, arg, must implement the tuple trait. The tuple trait is automatically implemented on all tuple types. So we have arg, which implements tuple, and g and f, which both implement fn once. The fn once trait is very complicated and part of a family of fn traits. Fn once represents a function that can be called once and only once. I will link its documentation in the description, which I would highly recommend reading because it is part of what I think is one of the most powerful design patterns in the Rust language. Note that the arg's generic on fn once must implement tuple. So g and f must implement fn once with arg as the generic and ret as the associated type. Basically, g and f must be functions with the same parameters and the same return type. The purpose of this function is to decide whether to call the runtime or const function. I will link the docs in the description where they explain its purpose and its downfalls. So we supply our pointer and two functions to const eval select, which chooses which one to execute and when it should be executed. Is_null has been conquered. We are in the home stretch of our deep dive into Rust's global allocator. It is clear that a lot of work has gone into this API, and I think the designers deserve tons of credit. Let's finish strong. So we've checked if pointer is null. If it is not null, we create a non-null pointer using the unchecked method. Quickly reminding you what new unchecked looks like. So we create a non-null pointer, verified to be non-null, wrap it in sum, and return it. If the pointer happens to be null, we simply return none, which indicates we could not construct our non-null pointer. That is how non-null verifies that the pointers it constructs are non-null. We now have either a valid non-null pointer or none. We use this method, OKOR, to handle the failure possibility. OKOR is a method that takes in an option and turns it into a result. If we feed it a sum variant, it returns an OK variant with the same data. If we feed it a none, it returns an error variant with the error we supplied. In this case, we supply it with the alloc error. This question mark operator means that if the result is an error, it immediately returns the value to the caller. Otherwise, it unwraps the value in the OK variant for use. Finally, we use slice from raw parts, as we have used it before, to create a wide pointer to the allocated memory block with our new non-null pointer and the size of the block. One last time, this is the function signature of slice from raw parts. We now have a valid non-null wide pointer to the allocated memory. We wrap it in an OK variant and return it to the function caller. So to recap, alloc_impl takes two parameters, layout and zeroed. Layout specifies the size and alignment of the requested memory, and zeroed specifies if the memory should be zeroed. The method returns either a non-null wide pointer to the requested memory block, consisting of its memory address and size in bytes, or an alloc error indicating an allocation failure. This method is called inside of the allocate method as part of the allocator trait implementation for the global struct. But allocator doesn't only require allocate to be defined, it also requires us to define deallocate. The method signature of deallocate takes the allocator itself, a pointer to the memory it wants to deallocate, and a layout that fits the requested block. This method is unsafe. I won't go into why it's unsafe or what conditions it must uphold, but I will of course link the allocator trait documentation in the description where they outline all of the safety requirements. We begin by ensuring that the layout size is not 0. We then convert the pointer into its raw form using the asPater method. Lastly, we call the dealloc function. Let's see what it does, even though technically you got a peek at it earlier if you were being extra observant. The dealloc function does the same thing as the alloc function. Call another function with pretty much the same parameters. Rust dealloc is actually one of the magic symbols from earlier. The compiler inserts the necessary deallocation method, which I will once again not be showing. Sorry. For the last time, let's zoom back out and explain how the function works. The deallocate function takes a pointer and a layout. These define what section of memory is going to be deallocated and what its size and alignment are. These two must coincide with each other, which is partially why the function is unsafe, among other reasons. Those are the two main functions that control the Rust global allocator that you see attached to every standard library collection. With that, We have successfully implemented Allocator for Global, a zero-size struct that controls the allocation behavior of arguably the most important data structure in Rust, vec. Thank you for watching. Next time, I'll go into detail about the operations of vec itself if that's something people would be interested in watching. Any recommendations or criticisms are extremely welcome. This is my first video, and I'm very excited to possibly make more. Comment what you'd like to see in the future, and hopefully, I will see you next time. This has been Behind Blue Screen. Be kind, and goodbye.